Okay, we're at the end of the videos associated with the introductory modules, and I always like to give just a quick summary of everything that we covered. So some of the things you need to remember from the introduction here is that distribution models are of two basic but not mutually exclusive formats. Typically, one of these is predictive output, what I refer to as a GIS map product. A second is an explanatory output that has an emphasis on ecological interpretation over map products. Now, the basic steps of a distribution model, and there are five of these that you need to keep in mind, are the articulation of an intended use, how one acquires data, vets it, and organizes it, how the SDM is actually constructed, how it's assessed, and how it is implemented. Now, I'm going to argue that this, of course, is the first, and this is the one you should spend the most time carefully thinking about, but all of them are crucial steps in building a defensible distribution model. Now, when exploring intended use, it helps to think about one or more of these four questions. Why is the element there? Where is the element located in space? How much of the element is there? And how is it changing over time? Now, I need to emphasize again, as I did before, that these are not mutually exclusive. And sometimes your intended use will include multiple components of these questions. One of the things you do need to keep in mind, however, is that at some point, if you have more than just a single one, you're going to have to prioritize them in a rank order as to which is the most important when making initial decisions about your proposed distribution model. Also, there's a host of somewhat ironic, funny, and yet at the same time incredibly true caveats that I don't want you to forget. The first, all models are wrong, some are useful. That is perhaps the most important one. Also, there's lies, damn lies, and statistics. This is kind of getting home to the fact that you need to be a little careful about the emphasis on statistics at times. And then, of course, even when you apply the statistical analysis, after 7.5 million years of analysis, this could mean waiting for a long-winded MCMC to occur, the answer might come back as 42. This is just a play on the words from Douglas Adams to point out that you can do all these machinations, but you still have to have a well-grounded distribution model in common sense and the ecology of the organism you're interested in. Now, articulating this intended use is the crucial first step. And associated with that is asking yourself, am I really interested in prediction or explanation? And where do these intended uses lie? Then this decision needs to be related back to those four questions I posed. That is, how much is it? Where is it? How's it changing? Why is it there? Because then that helps set the foundation for the decisions you'll make. In terms of classification models, you'll be exposed to parametric, semi-parametric, and non-parametric. The most modern are the non-parametric, and these are the ones most typically employed, but these both have strengths of their own, and that we will explore during the course. Which classifier you select depends on the intended use, the data characteristics, and statistical considerations. When it comes to classification, We're dealing with data that consists of presence only. We saw historical older forms of models that allowed you to explore just presence only data. But the strength of the classifiers we now employ rely on having a presence and a true absence associated with it. Now, absence can also be a generated pseudo absence. But again, you need a presence and absence, whether it be true or pseudo, so that you can employ the classifier. I also want to reiterate is that there's no best statistical model, although it is true that some models perform better given a intended use and data characteristics. In short, this perform better is conditional upon you having adequately described an intended use and explored the characteristics of your data. Last, decision risk is going to occur at all steps in a distribution model. It helps to label the decisions you make and the risk associated with each as either philosophical, technical, or intractable. These are obvious. If you don't have sufficient data to do anything, it's intractable. Technical, typically these can be resolved. This may require that you do an extensive literature search to document why you made the decision, say, for example, selecting a particular way of calculating a threshold, something like that. Philosophical are a bit harder to deal with, but you just have to at least listen to opinions before you select one. It's important to realize that there is no single analytical process that is going to eliminate decision risk. You can, however, minimize it with careful consideration of the basis. And last, one of the things that I hope to have you learn in this course is how to employ a structured process that documents all of the decision modeling points to minimize your decision risk and ensure that you have a defensible distribution model to apply to any conservation and management question. And then again, hopefully by Friday afternoon, you are going to be able to be conversant in the philosophical and ecological underpinnings of distribution models. You will have learned how to acquire, organize, and evaluate response and predictor data with an emphasis on true presence absence versus presence only data, an emphasis on understanding the relationships of environmental and geographic coverage on sample frames, pre-analysis strategies for exploring characteristics of your data. Once you pass through this stage, you'll be able to know how to apply sets of different statistical methods to build predictive models. Once the models are completed, how you evaluate and assess them, and an estimation of their uncertainties, and then looking at decision risk associated with it. And then we'll be able to construct and evaluate and present ensembles of the data output. In short, everything boils down to graphs like this. You're going to take data that you've organized, vetted, and acquired, create models like this, and buried underneath here are even some more. And if you look at some of the probabilities, what you're going to see is there's some kind of central tendency. And then when you move into the ensemble world, you can start to see, wow, look at this. Everybody's clustering here. Darker means 5 of 5 models are predicting in the same location. Here, darker colors mean higher likelihoods of plant presence. Here is darker colors has lower error. So in essence, by implementing this structured process and taking you on up to this concluding point here of ensembles, you should be able to walk into the decision environment with your models and say, listen, folks, given the intended use and how we approach this, these represent locations that we have to be concerned about in making the conservation and management decisions associated with the species. So this is what you're going to be able to do by the end of this course at 12 noon on Friday. And I want to point out here, since we're at the end of the summary, that there will be a short review of the introductory material. Chelsea and I opted to record all of this to provide more time for you to actually have hands-on coding. And it's important, hopefully, if you're listening at the end here, hopefully you gain some things so that when we walk in on Monday, we can dive straight into the course. Associated with this, if you have any questions after watching these videos, please feel free to send them to me at this email before we arrive at NCTC, or write them down on a piece of paper and bring them with you on the first day of class. And with that, we're at the end of the whole introduction, and I actually look forward to meeting everybody at NCTC in a couple of weeks. Take care and see you soon. Bye.